Hello, I'm Bryce Adelstein Lelbach. I started programming a decade ago, and I've spent most of that time working in HPC and on the C++ programming language. I'm the chair of the Standard C++ Library Evolution Group, which designs and standardizes the C++ standard library. I also chair the American Committee for Programming Language Standards and serve as editor for the Inclusive Terminology Guidelines for the Insights Standards body. I work at NVIDIA, where I lead our strategy for HPC programming models, C++ compilers, and C++ libraries. Previously, I worked at Lawrence Berkeley National Laboratory. I started my career under the tutelage of Hartmut Kaiser at Louisiana State University, where we worked together on the HPX parallel programming framework. Today, I'm going to talk to you about the C++ Committee's plan for bringing parallelism, asynchrony, and accelerated computing into standard C++. First, a few conventions used throughout these slides in the interest of brevity. We'll use these namespace aliases throughout the talk. This talk makes liberal use of class template argument deduction, also called CTAD. Standard C++ has always supported the deduction of template arguments when calling a template function. But in C++ 17, we extended this to work for class templates when calling their constructors. For example, when constructing a tuple, I don't need to spell out what the types are. They can be inferred from the arguments. Likewise, when constructing a std array, the element type and size can be inferred. The barrier to entry to parallel programming is far too high. We live in a world where almost all hardware platforms are parallel and require explicit programming to utilize that parallelism. Despite that, many users and many code bases do not utilize parallelism. For those that do, many have chosen approaches that are not portable to accelerators such as GPUs. So, the C++ committee wants to build an on-ramp to parallel programming. We want to give users easy-to-adopt solutions that are universally portable. We're not aiming to expose all the capabilities of each platform. We want widespread adoption and normalization of parallelism across the C++ ecosystem. What aspects of the C++ language itself makes it portable? If we asked a typical C++ programmer, I think we'd get a list that looks like this. Non-8-bit bytes, variable-sized built-in types, non-2's complement integers, non-IEEE floating point, non-Indian pointers, aligned addressing, segmented memory, etc. C++ supports all of these things. In the 20th century, that was the correct answer because implementation freedom was important in these areas. But very few of these things matter today. The industry is settled on solutions. Bytes are 8 bits, integers are 2's complement, floating point is mostly IEEE. Due to the strength of inertia, the cost to making a platform that doesn't conform in these regards is prohibitively high. So if most of this doesn't matter anymore, what does? What actually makes C++ portable? The answer is concurrency, parallelism, and asynchrony. That's the new portability contract of C++. That's what makes C++ portable today. The memory model, the execution model, forward progress guarantees are concurrency primitives. They're carefully designed to support essentially any platform, from tiny microcontrollers to server CPUs to GPUs and other accelerators. There's two parts of this contract that we expect to significantly evolve over the course of the next 2 to 4 years. Our story for parallel programming and our model for asynchrony. And that's what I'm going to tell you about today. There's something important that I want you to understand about the nature of the standard. The C++ standard is descriptive, not prescriptive. It does not prescribe exactly how everything is implemented. It describes the structure of C++ source code, the semantics of the abstract machine that executes said source code, and requirements on how that abstract machine is implemented. The standard specifies enough to be portable and consistent across platforms and domains. But the standard also grants enough freedom for each platform to choose the right design for their implementation and environment. We call this implementation freedom. It's essential to standard C++. I think many people don't appreciate the value of this. If we tried to specify everything and didn't leave room for implementation freedom, C++ would be less portable, not more portable. C++ would be less performant and less flexible. Some platforms might not even be able to implement standard C++. Implementation-defined and undefined behavior are often a feature, not a bug. The C++ standard's more what you'd call guidelines than actual rules. It's descriptive, not prescriptive. It grants a great deal of implementation freedom, and that's a good thing. That's what allows C++ to be portable and performant on so many platforms and environments. Some languages build facilities like parallelism into the core language itself. We don't do that in C++. Parallelism in standard C++ is exposed as a library feature. There's no language features for parallelism in what I'll present today. We have modified the C++ abstract machine model over the years to support parallelism and concurrency, but we expose that functionality through the library, not the language. We prefer to build library abstractions when we can. When we can't, we build the language features that enable us to build the library abstractions that we want. Some library abstractions may be implemented with compiler support under the hood, but that's just a detail. C++ is already a complicated language, and new language features almost always bring additional complexity and caveats. Library abstractions can be complicated, but they all follow the same set of rules, giving them some degree of uniformity and consistency. Compare C-style arrays to std arrays. C-style arrays have a bunch of odd quirks. You can't return them from functions, they decay to pointers, they have a special declaration syntax. Std array, on the other hand, is a class and follows the same rules as other classes. There's 3 pillars to our strategy for parallelism in standard C++. First, we need a corpus of common algorithms that dispatch to vendor-optimized parallel libraries. Next, we need tools to write your own generic parallel algorithms that can run anywhere. Finally, we need mechanisms for composing parallel invocations into task graphs. We'll start with the first pillar, the collection of common parallel algorithms. C++ has had a set of serial algorithms for manipulating sequences of objects since the first standard. These algorithms operate on one-dimensional sequences. Initially, they were parameterized with iterators, but with C++20, we've introduced a new, more powerful abstraction, ranges. There's about 100 different standard C++ algorithms. For loop abstractions, filters, sorts, searches, rotations, reductions, scans, etc. In C++17, we introduced parallel versions of these algorithms. The parallel overloads have the same interface as their serial counterparts, except that they take an extra parameter, an execution policy, which describes what form of parallelism is allowed, if any. Execution policies describe the how of execution, but they don't specify where. That's left up to the implementation. Execution policy parallelism could be implemented with a variety of strategies, such as a bespoke CPU thread pool, OpenMP, or GPU acceleration. Execution policies permit parallelism, but do not require it. An implementation may choose to not parallelize. The execution policy overloads are all fork-join synchronous. The implementation will wait for the parallel operations to complete before returning from one of these algorithms. Today, we have 4 execution policies. Seek indicates that all operations must be performed within the calling thread and must be indeterminately sequenced. Basically, it says no parallelism is allowed. Unseek also requires all operations to be performed in the calling thread, but allows those operations to be unsequenced with respect to each other, meaning that vectorization is allowed, but not required. PAR allows the implementation to parallelize operations at its discretion. It does not require parallelization, it simply allows it. However, it also requires that all operations within each thread are indeterminately sequenced, meaning that vectorization is not allowed. PAR unseek allows operations to occur in multiple threads and to be unsequenced with respect to each other, meaning that both thread and vector parallelism is permitted. Again, this means parallelism is allowed, not required. The implementation may choose to not parallelize. Let me show you one of my favorite parallel algorithm examples, word count. We can write it with a single parallel transform reduce. Transform reduce takes both a transformation operation and a reduction operation. It applies the transformation to the inputs and then uses the reduction to sum the results of those transformations. If you're familiar with MapReduce, this is C++'s form of it. We'll use the overload of transform reduce that takes two input sequences in a binary transform function. The first input sequence will be the entire string except the last element. The second input sequence will be the entire string except the first element. This means our binary transform function will be passed a window of every two adjacent characters in the string. Our transformation function's job is to tell us whether the two adjacent characters it's looking at are the beginning of a word. If the left character is white space and the right character is not white space, then the right character is the beginning of a word. The pseudo sequence produced by the transformation will look like this. For every word, one and only one of the transformation invocations returns true. But what about the first character of the string? We never actually test it with our transformation function. We start at the second character. So, we account for the first character in the initial value of the reduction. Our reduction operator is just plus. After the transformation, we have a sequence of bools. Summing that sequence into an integer will give us the word count. This standard C++ code is parallel and portable. You can run it anywhere, on your GPU, your server CPU, your laptop, even your phone. In C++20, the standard library introduced ranges. Unlike iterators, ranges are composable. Ranges allow us to express a wide range of algorithms in terms of a few key primitives. Used in conjunction, C++20 ranges and the C++17 parallel algorithms are quite powerful. Standard C++ algorithms iterate over sequences of objects, for example, the elements of a container. However, sometimes we want to iterate through indices instead of objects. This is particularly important in numerical and scientific computing. We can do this using iota, a range factory introduced in C++20. It produces a range of monotonically increasing integers. For example, iota 1n will produce a range of all integers from 1 to n minus 1. Instead of passing iterators to a container to a parallel for each, we can instead pass an iota range, giving us a parallel for over indices instead of objects. We can also use parallel algorithms and ranges to iterate multidimensional index spaces. C++23's Cartesian product range adapter takes multiple input ranges and produces a range of all the ordered tuples formed by taking an element from each of the inputs. We can use this in conjunction with iota to create ranges representing multidimensional index spaces. For example, here we use this pattern to write a simple parallel matrix transpose. The range V will produce two element tuples from 0, 0 to n minus 1, m minus 1. The iteration order will be row major. The second index will be contiguous. we can change to column major by switching the order of the arguments to Cartesian product. The C++17 execution policy parallel algorithms are fork-joined synchronous, so each invocation launches its work in isolation and blocks until that work completes. So, for example, if we invoke two parallel for eaches on the same data back to back, we'll get two parallel work launches. The caller will be blocked waiting for the first invocation to finish. Only then will the second invocation be queued and launched. This transfer of control back to the caller is a latency bubble and can degrade performance. One way to address this problem is to fuse the operations together into a single parallel invocation, which can be done with the transform range adapter. Transform takes an input range in a function and returns a range that is the result of applying the function to the input. This is completely lazy. The function is only evaluated as needed when the elements of the returned range are accessed. For example, here, f is not evaluated until the elements of v are accessed in the parallel for each. There is a big change in semantics here. Previously, we had a guarantee that all invocations of f would happen before any invocations of g. We no longer have such a barrier. Another useful range adapter is filter, which takes an input range in a predicate function and produces a range of all elements of the input for which the predicate returned true. Again, this is done lazily. The predicate isn't evaluated until the elements of the returned range are accessed. Here, we use filter in combination with a parallel reduction to sum only the positive elements of a container. The C++ parallel algorithms introduced in C++17 are great, but they're just the start of the story. They have two major limitations. First, the C++17 parallel algorithms are all fork-joined synchronous. They launch the parallel work, and then they wait until that work is completed before they return to the caller. Now, where exactly do they launch that parallel work? That's the second problem. By design, users have no control or visibility into where the parallel work runs. It happens in some amorphous implementation-defined execution context. It could be a CPU thread pool, a GPU stream, Grand Central Dispatch, Windows fibers, etc. Implementations have complete freedom. Today, C++ has no standard model for asynchrony and no standard way to express where things should execute. But the solution is coming soon to your C++ implementation. Senders and receivers, an asynchronous execution framework for standard C++. Let's look at a simple example. First, we need to get a scheduler from somewhere, from a thread pool, a tasking system, a GPU driver, etc. To start a chain of work on the scheduler, we call schedule, which returns a sender. That sender will complete on the execution context associated with the scheduler. Next, we use a sender algorithm, then, to compose work onto the sender that we got from the scheduler. This work will be performed on that same execution context. The sender algorithm will return a new sender, which we can use to add more work onto the chain. Finally, we wait until the chain of work has completed using sync wait, which will return the value sent by the final sender in the chain. There are three key concepts in this model: schedulers, senders, and receivers. Schedulers are handles to execution contexts. Schedulers produce senders. Senders represent asynchronous work that will eventually send a signal. They can be composed together with sender algorithms to form task graphs. Receivers process asynchronous signals from senders. Let's look at schedulers in more detail. I said they are handles to execution contexts, but what exactly does that mean? An execution context is a resource that represents the place where execution will happen. This could be a concrete resource, like a specific CPU thread pool, or a GPU stream. It could also be a more abstract resource, like the current thread of execution. Execution contexts don't necessarily have a representation in code, and today they don't have any exposed interface. They may have state associated with them, OS handles, memory, metadata, etc. Schedulers represent a strategy for submitting work to execution contexts. They are lightweight, non-owning handles to contexts. Schedulers are cheap to construct and pass around. Execution contexts hold all the state. Multiple schedulers may refer to the same execution context, including multiple different kinds of schedulers. For example, you might have two schedulers that submit work with a different priority. You might even have a scheduler that dispatches work to multiple different execution contexts. We use schedulers to produce senders that will perform work on the execution context associated with the scheduler. Once we've obtained a sender from a scheduler, we can compose work on it. Next, let's look at senders and how we actually compose them. As I said before, senders represent asynchronous work. They form the nodes of an asynchronous task graph, which may span multiple schedulers and multiple execution contexts. Senders are lazy. You must explicitly start them. When a sender's work completes, it sends a signal to the receiver attached to it. Receivers are handlers that get notified with a signal by a sender. There are three different handling paths, which are called channels. The value channel is used to indicate successful completion and may pass one or more values to the receiver. The error channel indicates that the sender's work failed and passes an error object that contains information about the failure. The done channel is used to indicate that the sender's work was canceled before it could be performed. This is distinct from the error channel because cancellation is not an error. It may happen during the course of normal operations. Each sender notifies its attached receivers with one signal, meaning only one of the three channels is invoked. Now, let's look at how senders and receivers are hooked up to each other. Let's start with some scheduler, which we will get a sender from. A receiver is attached to a sender via connect. This is a behind-the-scenes interface that won't usually appear when using asynchronous operations. Connect returns an operation state, which contains the actual work that the sender represents. Eventually, you initiate the work by calling start on the operation state. After some time, the operation completes, and then notifies the receiver with the signal. Next, let's look at sender composition. We compose together senders using sender algorithms, of which there are a few forms. The first is sender adapters. Sender adapters take one or more senders as parameters and return a sender. Most sender adapters are pipeable, just like range adapters. The semantics are similar to Unix shells. Send pipe F pipe G is equivalent to G of F of send. Languages like Haskell and APL call this point-free style. The primary input argument is not explicitly named. This syntax is essential for elegant composition of senders. Composing senders via nested function calls is a mess. The order in which operations occur is inverted from the order in which they appear in code. The predecessor senders are more deeply nested and thus appear after their ancestors. Things get a bit clearer when we instead use a temporary variable for each stage of the composition. However, this is error-prone. It's easy to mix up one of those named variables. The pipe syntax gives us a clean way to compose chains of senders in the order that they will be evaluated. Now, let me show you some of the most important sender adapters. Then takes an invocable, f, and calls it with the values sent by the prior sender. The sender returned from then will send the results of the invocation of f. This is how you attach a continuation to a sender. Bulk is similar to then. It evaluates the invocable once for every index in the shape n. In the simplest and most common case, the indices are one-dimensional and start at 0, and the shape argument is an integer indicating how many invocations to perform. The sender returned from bulk will pass along the signal from the prior sender. Transfer changes the scheduler that will be used for the next sender. It doesn't change the scheduler for the prior sender. Some senders can only be connected to a single receiver. For example, because they move any values or error they send instead of copying them. We call these one-shot senders. Senders that can be connected multiple times are called multi-shot senders. Split takes any type of sender and returns a multi-shot sender that passes along the signal from the original sender. Split senders represent forks in a sender task graph. Conversely, when all takes multiple input senders and returns a single aggregate sender that will send the signals from all of the inputs. Senders returned by WinAll do not have a scheduler associated with them, which means they do not promise where they complete. WinAll senders represent joins in a sender task graph. WinAll is not a pipeable sender adapter, as the partially applied piped form would be ambiguous with the fully applied non-piped form. Ensure started connects and starts a sender, returning a new sender that will pass the signal sent by the original. If the input sender is a composition containing other senders, those senders will be connected and started as well. Sender factories are another kind of sender algorithm. They do not take senders as parameters, but they do return a sender. Sender factories are used to start new chains and graphs. The senders they return are the root nodes. We've already seen one scheduler factory, schedule, which returns a sender that completes on the specified scheduler. The returned sender doesn't send values or represent any actual work. It's just a handle you can use to compose work on the scheduler. Just is another sender factory. It takes a set of values and produces a sender that will send those values immediately when connected. The last kind of sender algorithms are sender consumers. They take senders but do not return senders. They typically launch a sender graph by connecting and starting it. They are the leaf nodes of sender graphs. Sync wait is a sender consumer and synchronization primitive that blocks until a sender completes and then returns or throws whatever was sent. The sync wait that you'll see in most examples will be in the stood_this thread namespace. This is a concrete form of sync wait that uses a blocking mechanism suitable for use in stood threads or the main thread. We imagine in the future there may be additional forms of sync wait, such as one that is suitable for use with fibers. Now, let's discuss the details of how sender graphs get formed. Suppose we have a single link in a chain of senders. We have an abstract before sender adapter on the left-hand side of this link, a concrete then adapter, and an abstract after adapter on the right-hand side. If we unroll the pipe syntax, we'll have something like this. We've got a before sender that came from somewhere. We create a then sender, which will contain the before sender and the function f. And we'll also create an after sender, which will contain the then sender. We'll end up with a nested structure of senders. At some point, we'll connect a receiver to the outermost and last sender. Each sender in the nested structure will connect a receiver to its child. This happens in the opposite order of sender construction. That will give us a nested receiver structure that's the inverse of the sender structure. A nested operation state structure is also produced and returned from connect. Eventually, we'll start that operation state. As the operations complete, they'll begin notifying their receivers with signals. When the before receiver gets its signal, it will notify the then receiver. If it's a value signal, the then receiver will invoke f with the value and signal the after receiver with the results of that invocation. Let's look at a more advanced example, a generic, asynchronous, and parallel inclusive scan. We'll write it as a pipeable sender adapter so that it can be composed with other sender algorithms. It'll take three parameters, a sender, which we'll expect to send the input as a range, an initial value, and the number of tiles to split the input into. We're going to use the classic two-pass parallel scan approach, which requires temporary storage for partial results communicated between tiles. We need to allocate this temporary storage asynchronously once the prior sender has sent us the input. So we'll chain a then sender onto the prior sender. In the body of the continuation, we'll create a vector to hold the partial results. We'll return both the input range and the vector. Next, we need to do the parallel pass, the downsweep. We'll use bulk to invoke the body of the pass for each of the tiles. The first thing we do for each tile is calculate the range of elements that belong to the tile. Then we take all of the elements in each tile and perform a local serial inclusive scan on them, which we do right here. Next, we need to propagate information between the tiles. The sum of each tile needs to be added to the elements of all preceding tiles. We've already computed that sum. It's the last element of the local inclusive scan. We store that result into the partials vector. Assignments to partials from different tiles may happen concurrently, but that's fine. Each tile uses a different and unique slot in partials, and no one reads from partials yet, so there's no data race here. Then, after all the tiles have completed their local inclusive scans and written to partials, we need to have one execution agent do a serial inclusive scan of partials. We do this by piping another then sender onto the chain, which will perform the partials inclusive scan. This then sender will again pass along the input sequence and the partials vector. The result of the scan over partials looks like this. The information that each tile needs to add to its elements is in the partials slot for the tile directly preceding it. Now we need to go parallel again to distribute that information within all tiles. This is the upsweep pass. So we'll pipe another bulk, once again over all tiles. In the body of this bulk, we'll need to calculate which elements belong to the current tile, just as we did before in the downsweep pass. Then we'll use a serial for each to increment each element in the tile by the appropriate value from the partials vector. After that addition, we'll have the correct result. Finally, we want the sender returned by our asynchronous inclusive scan to only send the input, not the partials vector. So we add a final then sender which only passes along the input. The partials vector will be destroyed when this then sender completes. And that's it. We're done. We've got a generic, asynchronous, and parallel inclusive scan that we can run on any scheduler we want. Senders and receivers are the next major step in the deployment of C++ standard parallelism. They deliver the second and third pillar of our plan. The framework gives us the tools we need to write our own generic parallel algorithms that can run anywhere and compose asynchronous task graphs. Following the standardization of senders and receivers, we'll introduce new asynchronous sender-based versions of the standard parallel algorithms. Today, C++ has no reasonable abstraction for multidimensional data. This is unfortunate, as many of the interesting compute-heavy problems that benefit from parallelism have a multidimensional shape. That's why we're introducing MDSpan, a multidimensional span type, in C++ 23. It's very similar to the one-dimensional span introduced in C++20. MD-span is non-owning. It's just a handle to some underlying data. It doesn't manage the lifetime of that data. MD-span is cheap to copy. It just contains a pointer and metadata describing the size and shape of the structure. Metadata such as the extent of a dimension can be expressed either at runtime or compile time, allowing for metaprogramming and compile time optimization. MD-span parameterizes how a multidimensional index is mapped to a location in the underlying data. We call this parameter a layout, and it can express any kind of multidimensional structure. There are some concrete layouts in the standard library for common use cases, but anyone can define their own layout and plug it into an MD-span. Likewise, MD-span parameterizes how it accesses the underlying data. The default is to just perform a normal C++ pointer dereference with an index. With a custom accessor, you could instead use a special cache bypassing instruction, read from disk, or perform a remote memory access. MD-span uses extents objects to express the number of dimensions in a space, the rank, and their length, the extents. Extents objects take a variadic number of integrals as template parameters. For dynamically sized extents, the magic value dynamic extent is used as a template parameter, and the extent is passed to the constructor. Through the power of C++20's class template argument deduction, when you're working with all dynamic extents, you usually don't need to spell out the entire verbose instantiation. There's also an alias, dExtents, for the all dynamic extents case. It takes a single parameter, an integral specifying the rank. For statically sized extents, the extent itself is passed as a template argument. No corresponding constructor argument is needed. You can mix static and dynamic extents. For example, in this case, we have one static extent and one dynamic extent. So we'll need to pass just one extent at runtime. Extents objects in MD-span support arbitrary rank. You can have as many dimensions as you want. MD-span has 4 template parameters, 2 of which are optional. The first is the element type. The second is the extents type. This must be a specialization of the extents class template. The third is a layout. The default is layout right. We'll discuss layouts more in a few moments. The final parameter is an accessor, which performs element access. MD-spans of all dynamic extents have a simple syntax. With class template argument deduction, you can construct one without specifying any template parameters. If you do need to spell the type out, it's still concise. Just use the dExtents alias. The elements of an MD-span are accessed via the index operator. Thanks to a recent core language change in C++23, indexing operators can now take multiple parameters. You can also make MD-spans of static or mixed extents. The simplest way to construct these is by passing an extents object as the second constructor argument. Now, let's talk a bit more about layouts. The 2 most common layouts are layout right and layout left. With layout right, the rightmost extent is contiguous, meaning its stride is 1, and strides increase right to left as the product of extents. This is the layout for C++ built-in arrays and NumPy. It's also the default for MD-span. For example, if we had a 2x2 matrix, the 2 elements on the first row would have data locations 0 and 1, and the elements on the second row would have data locations 2 and 3. With layout left, the leftmost extent is contiguous. Its stride is 1, and strides increase left to right as the product of extents. This is the layout used by Fortran arrays and by MATLAB. If we had a 2x2 matrix in layout left, the two elements in the first column would have data location 0 and 1, and the two elements in the second column would have data location 2 and 3. There's also a standard layout that allows you to explicitly specify the strides for each extent. All three of the concrete layouts in the standard library are just implementations of the layout concept. Generically, a layout is just something that maps a multidimensional index to a data location. Anyone can define a layout. Layouts may be non-contiguous. They may map multiple indices to the same location. They may perform complicated or expensive computations. And they may have or refer to state. Parameterizing layout is critical because it allows us to write generic multidimensional algorithms that can be used with any layout. This is an essential component of portability because different layouts may be needed on different platforms to deliver on performance. Today, we have a major vocabulary problem with multidimensional types in the C++ ecosystem. Suppose I write a function that uses a concrete owning multidimensional type like eigenmatrix. My users will be able to pass an eigenmatrix to this function. But what if they have a boost uBLAS matrix, or a PETSI matrix, or a Blaze matrix, or a cutless tensor, or a multidimensional array passed from Fortran? That's where MDSpan comes in. By using it in your interfaces, your code can work with any multidimensional data structure. Because MDSpan is just a non-owning handle, you can construct one that refers to an eigenmatrix, a boost uBLAS matrix, a PETSI matrix, a Blaze matrix, a cutless tensor, an array from Fortran, a built-in C array, etc. Now, let's look at some examples. For example, suppose we had our own row major matrix class. We can add a simple MDSpan conversion operator, allowing us to pass our matrix class to any interfaces that expect an MDSpan. In some more complex cases, we might have to write our own layout type. Now, let's look at how we can use MDSpan. This is a simple 3D 7-point stencil inner kernel, similar to what you'd see in a proxy application like MiniGhost. We have two 3D MDSpans representing the problem state. Using the Cartesian product of iotas technique I showed earlier, we build a range iterating the index space, and then use a parallel for each to iterate that space. If we want to change the layout, all we have to do is change the input MDSpans. Everything else remains the same. Earlier, I showed you this example of a simple parallel matrix transpose. We used span and dealt with the multidimensional indexing manually. That's not particularly portable. We've hard-coded a specific data layout, which may not make sense in all circumstances. It's also error-prone, as it's easy to make a mistake in the indexing formula. We can improve this by using MDSpan instead. Now we can change layout by simply changing the type of MDSpan that we use. I'm fairly happy with the last slide, but I want more down the road. I'd like to be able to write something like this. There's three things here that we don't have yet. Parallel algorithm overloads that accept ranges directly instead of iterator pairs, an indices method on MDSpan that returns a range of its multidimensional index space, and a language extension to destructure tuples and parameters. Going a step further, I want the asynchronous version of this that parameterizes where it runs. MDSpan has a powerful slicing interface, sub-MDSpan. It takes an MDSpan and returns a sliced MDSpan. Because MDSpan is non-owning and cheap to copy, slicing is also cheap. You're just creating a new view of the same underlying data. The input MD span is not modified. For each extent of the input MD span, you pass a slice specifier to sub-MD span. There are 3 kinds of slice specifiers. You can specify a single index to be selected for an extent by passing an integral as a slice specifier. The rank of the returned MD span is reduced by 1 for each single index slice specifier. You can also pass a range of contiguous indices to be selected for an extent. Finally, you can pass full extent to select an entire extent. For example, here we have a 3D MD span, M0, and we make a slice of it by selecting 8 indices for each extent, starting at indices 16, 32, and 8 respectively. The MD span returned by sub-MD span, M1, will have a rank of 3. We didn't use any single index slice specifiers, which would cause a rank reduction. Each of the extents of M1 will be 8. Multidimensional indices for M1 will be offset from what they would be for M0. For example, M1000 would be equal to M0 16, 32, 8. Let's look at another example, this time with rank reduction. We'll slice M0, selecting index 16 for the first extent, the entire second extent, and index 32 for the third extent. The MD span we produce, M2, will have rank 1. And the extent of that rank will be 128, the extent of the second dimension of M0. Iterating this 1D slice will be equivalent to accessing M0 with a fixed index for the first and third extent. Sub-MD span is a useful tool for writing tiled algorithms. Let's build a tiled version of the parallel matrix transpose we looked at earlier. We'll work with square tiles with extent t by t. First, we need a range describing the set of all tiles. We'll again use a Cartesian product of iotas for this. It's okay if the tiles at the edges extend beyond the bounds of the matrices. We'll handle that in a moment. Then we have our parallel for each. This time, it's going to iterate over the tiles, not all of the indices. For each tile, we're going to create new sliced MD spans for A and B using sub-MD span. First, we need to determine what range of indices we need to select based on the coordinates of the tile. This is where we handle tiles that would go beyond the bounds of the matrices. We just truncate them to the ends of the matrices. Now, we'll pass the tuples describing the indices we want to sub-MD span, producing the local MD spans for this tile. Next, we need a range of the multidimensional indices within the tile. Finally, we use a C++ range-based for loop to iterate over the indices of the tile and perform the transpose with the local MD span slices we made. With that, we're done. The set of standard C++ algorithms we have today is great, but not complete. What we have is primarily focused on manipulating one-dimensional sequences of objects. We only have a very limited set of numerical algorithms, such as reductions and scans. We don't want C++ programmers writing their own versions of common numerical algorithms. We want them to use standard interfaces that are backed by an implementation designed and optimized for the platform they are running on. So, the C++ committee is exploring new families of algorithms to standardize, starting with linear algebra. The C++ committee doesn't want to reinvent numerical linear algebra. We standardize existing practice, and the existing practice for linear algebra is BLAS, the basic linear algebra subprograms. We want to standardize a modern C++ interface that can be implemented under the hood by existing BLAS libraries. The existing one-dimensional C++ algorithms parameterize data with iterators, and since C++20, ranges. For standard C++ linear algebra algorithms, we plan to parameterize data with MD-spans instead. We use the MD-span parameters to express things that appear as distinct parameters in traditional C-style BLAS interfaces. For example, instead of having scaling parameters on matrix vector product, we have a scaled operation that takes a scaling factor in an MD-span and returns a new MD-span that will apply the scaling factor upon access. C++ standard library implementations can see through this abstraction and extract the scaling factor to feed it to a lower level BLAS interface that expects it. Another example is transposed, which returns a transposed version of the supplied MD-span. As with today's C++ algorithms, we're planning to have serial and fork-joined parallel overloads of linear algebra algorithms. In this example, where we solve a system via upper triangular Cholesky factorization, we'd want to chain the two operations together and launch them asynchronously. In the future, we imagine we'll have asynchronous sender-adapter forms of these algorithms that will allow you to do that. There's plenty of other work down the road for C++ standard parallelism. Other classes of numerical algorithms, asynchronous streams, memory model extensions, affinity and locality facilities, etc. But with every standard revision, we deliver more and more components of C++'s story for parallelism. I want to end where we started, with our goal. We need on-ramps to parallelism in standard C++. Almost all modern platforms are parallel, yet a shocking amount of code does not take advantage of that parallelism. So, we want to normalize parallelism and accelerated computing. Writing parallel C++ code should be easy and natural. Parallelism should be the default. Thank you all for your time. I hope to see you in person at next year's conference.